A very good morning to everyone who's watching this video right now, including our lecturer, Madam Rohaya. This video is about our Assignment 2, that is the converter. So these are the team members of Group 7, that is Tonny, Tang, Chong Kar Min, Tracy, Liaw, and Wei Jie. In this video, we'll be talking about the programming source code and the program execution.
Now, we will start off from the programming code.
So, good morning to Madam. My name is Wei Jie with matrix number 289669. So, I will start presenting about our result of our works about the SCQM1103 Assignment 2. So, in the first page of our system, there is a menu page. There is two items in the menu page, which the combo box 1 and combo box 2, each in the right side and the left side. So, in the left side, you can click on the combo box and either choosing positive decimal, binary, negative decimal, or floating point binary. So, in the right side, you can either choose binary or decimal. Each of the choice will lead you to the different frame. So, for example, if the left side of the combo box, if you choose the positive decimal, and the right side you choose the binary, it will lead you to the first frame and allow you to convert the positive decimal to binary. So same, if you want to change negative decimal to binary, you can also either click on the negative decimal on the left side and binary to on the right side. So for the first question given in the assignment, we are needed to convert the positive decimal to binary digit. After receiving the decimal number typing by the user, it will directly change to the binary number by using the code long.to binary string. In this frame is actually purposely designed for positive decimal only. So if the user enter any negative decimal, the system will display an error message warning the user to input positive decimal only. On the other way, if the user enter the positive number, the decimal entered by the user will be directly changing to the binary and will be displayed out. So for the question 2 in the assignment, we are required to design a system to convert the binary to decimal number. So after the user enter the binary number, then the binary number will be placed in an array with 8 bits. So for the first place in the array, it will store the first bit, and until the last 7 place in the array will store the last 8 bits. After the value is stored in the array will undergo a for loop to decide the value of the decimal number. For the first place in the array, it will decide the decimal to be positive or negative. If the first place in the array is 1, then the decimal number will start with negative 128. If the value of the first place in the array is 0, then the decimal number will start with 0. And for the second place to the 8th place, the decimal number will sum with the value according to the position of current array. So for example, if the second value in the array is 1, then the decimal number will plus with the value of 2 power of 6, which is 64. And for the last place in the array, if the value is 1, then the decimal number will plus with the value of 2 power of 0, which is 1. For any value in the array, if the value is 0, the decimal number will just plus with 0. So that's all for my presentation part. I will now pass to Tonny Tang.
My name is Tonny Tang, number matric 284990. Next, I will explain the question 3 and question 4, which are negative decimal to binary converter and floating point binary to decimal converter. Firstly, we will convert the user input string value to decimal value. If the decimal is more than 0, we will use J option pen to alert the user that only negative decimal is allowed. In contrast, if the decimal value is less or equal to 0, we will calculate the absolute value of decimal by using formula decimal minus decimal times 2. Next, we will declare an array to store the absolute binary value. In the for loop, we will continuously divide the absolute value of decimal by 2. If the result is more than 0, the system will perform result mod 2 operation to get the remainder and store it into the array until the result eventually becomes 1. This is how we get the absolute of binary value. Next, the system will perform first complement operation. In the for loop, if the value of absolute binary is 1, the system will convert 1 to 0 and vice versa. Lastly, the system has to perform second complement operation by adding 1 with the first complement binary. If one of the elements of the second complement array is more than 1, which means it's 2, after the addition of 1, this element will change back to 0 and the next element will plus 1. Unless it is the last element in the first complement array, then the last element just change back to 1. At last, the system will convert the value of first complement and second complement array into string format and set them into the test file respectively. Next, I will continue to explain the source code of question 4. The system will use a string method to divide the birth or 16 bits binary string into 2 different length of strings, according to the number of mantissa and exponent bits. Next, the system will first calculate the decimal value of exponent. The system will create an array with the size the same as the number of exponent bits. In the for loop, if any of the elements in the array is 1, the system will from net.power a power of 2, where a is the location of element in the array and eventually sum out to become the exponent value. After we getting the value of exponent, the system will use big decimal class to move the floating point of mantissa to leftmost. If the exponent is positive, the system will use that string method to divide mantissa into mantissa 1 and mantissa 2 according to their floating point after shifting. Next, the system will create an count n1 array to store the elements of mantissa 1. The system will continue to convert the mantissa 1 into decimal by using left.power b power of 2, where b is the location of each element in the count n1 array. For the sign bit, which is the first element in count n1 array, if the sign bit is 1, the system will minus the decimal value of mantissa 1 with the result of net.power b power of 2. In contrast, if the sign bit is 0, the system will plus the decimal value of mantissa 1 with the result of net.power b power of 2. Next, we are counting the second part of the mantissa. We are doing the same thing just like to calculate the decimal of first part of mantissa. Firstly, we will create and count n2 array to store each digits of second mantissa. For each of the element in count n2 array, the system will plus that n2 with result of 1 divided by net.power I plus 1 power of 2, where I is the location of each element in count n2 array. Lastly, we will sum out that n1 and that n2, and this is the final result for our decimal value. And the system will set it to the decimal test field. In contrast, if the value of exponent is negative, the system will use big decimal class to move the floating point of mantissa according to the exponent. The system will create and count an array to store each of the digit value of the mantissa. Next, the system will convert the mantissa into decimal by using 1 divided by net.power I minus 1 power of 2, where I is the location of each element in the count n array. If the sign bit, which is the first element in the count n array, is 1, then the system will minus the decimal with 1 over net.power n minus 1 power of 2. In contrast, the system will plus. Lastly, the system will convert the double decimal m into string, set it into the decimal test field. That's all for me. Thank you.
My name is Chong Kar Min, number metric 2801173. Now I will proceed with the program execution. This is the main interface for our program. There are 4 combo blocks for the from, which is positive and negative decimal, binary and floating point binary, and 2 combo blocks for the to, which is binary and decimal. So I will show you how to run our program for the question number 1 and question number 2. For the question number 1, which is convert the positive and negative decimal number to 8-bit binary. So for the question number 1, we will choose the from combo box, which is positive decimal to binary. Then we click continue. We will jump to the positive decimal to binary converter and enter a positive decimal number, which is 22. Then click convert. The binary number is 10110 and 8-bit binary number is 0001010. Then we click the back button. We will come back to the main interface of our program and we choose negative decimal and to binary. We'll jump to the negative decimal to binary converter and enter a negative decimal number, which is negative 22, and then click convert. The absolute binary number is 0001010. The first complement is 1110101. The second complement is 1110110. Then we click the back button. We will jump back to the main interface of our program. For the question number 2, which is convert the positive and negative binary number to decimal number. So we will choose for the from combo box, which is binary, and to combo box, which is decimal. Then we click continue. We will jump to the binary to decimal converter and enter a positive binary number, which is 01110011, and click convert. The answer is 115. For the negative binary number, which is 11001110, then the answer is negative 15. That's all from me. I will pass it to Tracy.
So next we'll be continuing on to the next question, that is converting the given negative decimal number into an 8-bit binary using 2's complement. From the main menu, we'll have to choose going from the negative decimal to the binary, continue, and now we've arrived to the conversion page. So entering the negative decimal, we'll be giving it a value of -7, convert, and we'll be receiving the absolute binary value is 01010111. The first complement is 10101000, and the second complement is 10101001. So now we've arrived to the last question, that is converting the floating point binary numbers into a decimal. From the main frame, we'll be choosing from floating point binary numbers to decimal, continue, and now we'll be arriving to the conversion page. And for this question, we'll be using 2 examples for the 16 bits and the 12 bits. So we'll start off with the positive 16 bits number. We'll be giving an input of 0110 1000 0000 0011, 10 bits of mantissa, and 6 bits of exponent. The output we'll receive is 3 for the exponent, 0110.1000 for the mantissa after shifting the floating point, and 6.5 for the decimal. Next, we'll be giving it a negative 16 bits floating point binary number. So the input we'll be putting is 1110 1000 0000 0011, 10 bits of mantissa, and 6 bits of exponent. The output we receive is 3 for the exponent, 1110 1000 for the mantissa after shifting floating point, and negative 1.5 decimal. Moving on, we'll be starting off with the 12 bits examples. First, with the positive 12 bits floating point binary number, we'll be giving it an input of 0101 000 1101, add bits of mantissa and 4 bits of exponent. So the output will be negative 3 for the exponent, and the mantissa after shifting the floating point is 0.001010000 and 0.078125 for the decimal value. For the negative 12 bits floating point binary number, we'll be giving it an input of 1101 000 1101, 8 bits of mantissa, and 4 bits of exponent. The output for this value is negative 3 for the exponent, 0.0011010000 for the mantissa of the shifting floating point, and negative 0.046875 for the decimal value. Thank you everyone for watching the whole video of our presentation.